Imagine standing on a bridge, maybe feeling the rumble of traffic, or just looking up at a huge skyscraper. What's holding it all together? What invisible forces are actually at work?
It's fascinating, isn't it? There are these hidden forces constantly working inside structures, allowing them to, well, defy gravity and handle massive loads.
And today, we're diving deep into one of those absolutely critical, though often unseen, forces, transverse shear.
That's right. This deep dive is really all about getting to grips with how forces push across a beam. This creates internal stresses.
Stresses that, if you don't account for them, could actually lead to failure.
Exactly. So we'll explore where these stresses build up the most, how engineers, figure them out, calculate
And
them,
what happens if they get it wrong?
and what happens then? Yes, we'll look at that too.
So our mission here is to give you a real shortcut to becoming, well, properly informed about shear mechanics.
We want you to get those crucial insights into structural integrity, maybe have a few aha moments.
Yeah, moments that might actually change how you look at buildings, bridges, just everyday structures around you, ready to get into these hidden dynamics.
Absolutely. Let's start with the basics. What is transverse shear? We often use the letter V for it.
How can be?
So it's an internal force acting perpendicular to the beam's length, right across its cross-section. But here's the really key thing. Because of something called the complementary property of shear, this force doesn't just push, say, down. It also generates a corresponding longitudinal shear stress.
Longitudinal, so along the length.
Precisely, along the length of the beam. Think about like a block of Jell-O. If you push down on top,
Right.
it doesn't just squish downwards, does it? It also tries to bulge out sideways. Shear is a bit like that. A force in one direction creates this internal sliding tendency in a perpendicular direction.
And you can actually see this happening in the real world, can't you? Like railroad ties.
Perfect example. They act as beams, and they take huge transverse shear loads from trains passing over.
And if they're wooden ties, you sometimes see them splitting, right? Horizontally, near the ends.
Yes, that horizontal splitting, that's a direct result of that longitudinal shear stress we just mentioned.
Ah, okay.
It's right there at the ends, near the supports, where the internal shear forces are often highest. That creates so much longitudinal stress that it can literally tear the wood fibers apart along the grain.
Wow. A pretty vivid demonstration, as you say.
It really is.
So, to really get our heads around this longitudinal shear idea, let's try a visualization. Imagine a beam, but it's not solid. It's made of, say, 3 separate wooden boards just stacked loosely on top of each other.
Okay, got it. Loose boards.
Now, if you push down on the middle of that stack, what happens?
Well, they'd just slide against each other, wouldn't they? The top one would slide one way, the bottom the other way, relative to the middle. They definitely wouldn't act like a single strong beam.
Right. But now, and this is the clever bit, what if you bond those boards together? Maybe with glue or nails.
Ah, okay, so now they're connected.
Yeah. What does the longitudinal shear stress do then?
Well, that stress is what the glue or the nails have to resist. It prevents that sliding. And because the boards can't slide anymore, the whole stack starts acting like one single, solid, and much, much stronger beam.
It's the same idea behind those little shear studs you see welded onto corrugated metal decking before they pour concrete, right?
Exactly the same principle. Those studs lock the concrete slab to the metal deck. They stop any slipping.
So it becomes a composite slab, stronger together.
Much stronger. It's a really fundamental concept in structural engineering, using that internal shear resistance to connect parts.
And this shear stress, it also causes some physical change in the beam, doesn't it? Like distortion.
Yes, that's right. As a result of shear stress, you get shear strains. And these strains actually cause the cross-section of the beam to distort slightly. It doesn't stay perfectly flat or plane.
It warps.
It warps, exactly. In a complex way, if you could draw tiny grid lines on the end of the beam before loading it, you'd see them deform after the load is applied, showing that internal sliding or warping.
Okay, so we've got transverse shear pushing across, longitudinal shear acting along the length, and this slight warping effect. But how do engineers actually calculate this stress? How do they put a number on it for design?
Right. That brings us to a really core tool,
Yeah.
the shear formula. You often see it written as equals VQ over it.
If EQE, okay, looks simple enough. Maybe.
Well, it's powerful, but the derivation is interesting. Unlike some stresses where you can figure out the strain distribution easily, shear strain is complex. So the stress, tau, is found indirectly.
So?
Engineers look at the horizontal forces acting on a tiny slice of the beam. They basically make sure everything is in equilibrium, all the pushes and pulls balance out.
And they make some assumptions.
They do. A key one, especially for long, slender beams, is that the shear stress is pretty much constant across the width T where you're measuring it, and that the warping effect we mentioned is small enough not to mess up the calculation too much.
Okay, let's break down that formula. VQI is the shear stress we want to find.
Right, the shear stress, usually thought of as an average value across that width T.
V is the internal shear force.
Yep, the total shear force inside the beam at that particular cross-section.
I is the moment of inertia. That sounds familiar from bending.
It is. It's the moment of inertia of the entire cross-sectional area, calculated about the neutral axis. It tells you how resistant the shape is to bending.
And the neutral axis is that line through the middle where there's no bending stress.
Correct. And T is just the width of the beam at the specific point where you're calculating the stress.
Okay. VIT. Now the tricky one, Q. What exactly is Q? It always seemed a bit abstract.
Yes. Q. It often trips people up. Mathematically, Q is defined as Y prime times A prime,
Yep.
where A is the area of the part of the cross-section either above or below the line where you're measuring the stress drive.
Right, the area is sort of hanging off that point.
Exactly. And U is the distance from the neutral axis to the centroid or the geometric center of that specific area A.
Mm.
Conceptually, you can think of Q as representing the moment of that area A. It's related to how much that piece of the beam is trying to slide horizontally relative to the rest of the beam just below it due to bending.
So it's kind of measuring the sliding tendency of that top or bottom chunk.
That's a good way to put it. It quantifies how much that area A is being held onto the rest of the beam by the longitudinal shear stress.
And the formula tells us that the maximum shear stress happens where Q over T is largest.
Generally, yes. Where that ratio Q reaches its maximum value within the cross-section, that's where you'll find the peak shear stress at max.
Okay, so typically VQI, it seems pretty fundamental, but you mentioned nuances, limitations.
Oh, absolutely. This is where the practical engineering side comes in. The formula assumes the shear stress is spread evenly across the width T.
That it isn't always.
Not perfectly. For instance, in a simple rectangular beam, the actual shear stress isn't uniform across the width. It's actually highest near the vertical sides and dips a bit in the middle of the width.
Really? How much difference does that make?
It can be significant. For a wide, flat beam, say, where the width is twice the depth, the actual maximum shear stress might be like 40% higher than what the basic formula predicts.
Wow, 40%. That seems like a big discrepancy.
It is, and the formula also isn't very accurate right at sharp corners or abrupt changes in the cross-section. Think about where the flange meets the web in a steel I-beam.
Stress concentrations.
Exactly. You get stress concentrations there, just like you do in bending. The formula doesn't capture those peaks very well. And you shouldn't really use it across a section that cuts the beam boundary at an angle other than 90 degrees.
So this raises a really important question then. If the formula has these known inaccuracies, why do engineers rely on it so heavily?
It's a great question. And the answer is about practical design and where failures are most likely to occur.
Okay.
While the formula might not be perfectly accurate at every single point, it does a very good job of calculating the average maximum shear stress. And for common shapes, like those steel wide flange beams, that maximum stress occurs at the neutral axis, right in the middle of the web. And in that specific critical location, the web is usually tall and thin, meaning the formula's result is actually very close to the true maximum stress.
So it's accurate where it matters most for design.
Precisely. Engineers use it to ensure safety against the most likely shear failure modes. It provides a reliable, predictable basis for design without getting bogged down in extreme complexity for every single point. It's a really smart engineering compromise.
So for example, if you're gluing two boards together to make a T-beam, you'd use the formula to figure out the shear stress in the glue.
Yes. You'd calculate VQite right at the glue line. Maybe you find the glue needs to handle, say, 4.88 megapascals to stop the boards from slipping past each other under the expected shear force V.
It's all about resisting that longitudinal slide.
That's the key. And think about timber beams again. We know the stress distribution is parabolic in a rectangle, peaking at the neutral axis.
Right. Max equals 1.5 times V over A, the total area.
Exactly. And wood is typically weak in shear along its grain, so where does it often fail?
With horizontal splits.
Often starting right through the neutral axis, especially near the supports where V is high. The formula explains why it fails there. That's where the longitudinal shear stress is highest, attacking the wood's weakest direction.
And for a steel I-beam or wide flange beam?
The distribution is different. You calculate at different points.
Mm-hmm.
It might be quite low out in the flange, jump up significantly where the flange meets the web.
And then be highest in the web.
Yes, highest near the neutral axis in the web. But what's interesting is that through most of the web's depth, the shear stress is actually pretty close to being uniform. It doesn't vary that much through the web height.
So it's concentrated in the web.
Very much so. Which is why some design codes actually allow engineers to simplify things further and just calculate the average shear stress across the web's area, V divided by the web area.
As a reasonable approximation for the maximum.
Exactly. Because the web takes almost all the shear and the stress within it is fairly constant, that average value is often close enough for practical design checks.
Okay, that makes sense. It's about practical application.
Right.
Now, we've talked about shear within a single solid piece, but often engineers build beams from multiple parts, right? To make them stronger or more efficient.
Absolutely. We call these built-up members. You might nail several boards together or bolt steel plates or weld sections.
But then you have the same potential problem as our loose boards earlier. They could slide relative to each other.
Precisely the problem. If those individual parts aren't connected properly, they won't act together as a single unit.
So you need fasteners. Nails, bolts, welds, glue.
Yes, and to design those connections, to know how many nails you need or how strong the weld must be, engineers need to figure out the force those fasteners have to resist.
And this brings us to shear flow.
It does. Shear flow, usually denoted by Q. Think of it not as stress, force per area, but as force per unit length along the beam.
Force per length. Okay.
The formula is very similar to the shear stress formula. Q equals VQ over I. Notice the T is missing from the denominator.
Ah, right. Q equals VQI. So it tells you the longitudinal force that needs to be transferred between parts per inch or per meter of beam length.
Exactly. It's the flow of shear force along the connection line. And this is incredibly useful for fastener design.
How so?
Well, imagine you know that one nail can safely resist a certain amount of shear force. Let's call it F.
Okay.
And you've calculated the shear flow Q, force per length, that needs to be resisted along that line of nails. Then you can figure out the maximum spacing S you can have between those nails. The force the nail resists, F, must equal the shear flow Q multiplied by the spacing S. So S equals FQ.
Ah, so you calculate Q, you know the strength F of your fastener, and that directly tells you how far apart you can place them.
Precisely. It ensures the fasteners are close enough together to handle the accumulating shear force and prevent any slippage between the connected parts.
Let's take that glued T-beam example again. Maybe it's a big beam with a huge shear force, say 850 kilonewtons.
Okay.
You could calculate the shear flow Q that the glue line has to resist. It might be a massive number, like 2.66 meganewtons per meter.
Wow, that's a lot of force per meter length.
Yeah. And if the T-beam has glue on both sides where the flange meets the web, then each glue seam only needs to resist half of that total shear flow.
Right, the flow splits between the connection points, so maybe 1.33 millimeter per seam. That tells you exactly how strong your adhesive needs to be.
Or think about a box beam made by nailing 4 boards together.
Okay, a hollow box shape.
If you know each nail can take, say, 150 newtons of force, you calculate the shear flow Q at different points along the beam where the boards are joined. Maybe near the supports, the shear flow Q is higher, so the formula S, of course FQ, tells you the nails need to be closer together, perhaps every 135 millimeters.
Right.
But further away from the supports, where the shear force V, and thus Q, is lower, maybe the required spacing increases to 225 millimeters.
So the nail spacing can vary along the beam's length, matching the shear flow intensity. And sometimes you might have two surfaces resisting the shear flow at a joint.
Like nailing through the sideboards into both the top and bottom board.
Exactly. In that case, maybe two nails are effectively resisting the calculated shear flow Q at that point, which would affect your spacing calculation.
And this really highlights how the way you build something matters, doesn't it?
Immensely. Imagine you have some boards and nails. You could arrange them in different ways to make a beam. Let's say you make one beam by nailing sideboards onto a central vertical board, like an I-beam. Then you make another beam using the same boards and nails, but maybe arrange it as a box.
Okay, same materials, different configuration.
Even if the nails have the same strength, F, the shear flow calculation, QV, QI, will give different results because Q and I depend on the cross-sectional shape.
Yeah.
Meaning, one configuration might be able to support a much larger overall shear force V than the other before the nails fail. Maybe the I-beam arrangement can only take 130 newtons of shear, but the box arrangement can take 400 newtons.
Wow, just by changing how you connect them.
Exactly. It shows how critical understanding shear flow is for designing efficient and safe built-up structures. The arrangement is key.
Okay, so we've got stress inside a solid piece and shear flow Q for connecting pieces. Now let's focus a bit more on this idea of flow, especially in what are called thin-walled members.
Right. These are common in aerospace, automotive, and even some civil structures. Think aluminum extrusions, thin steel channels, things where the wall thickness is small compared to the overall dimensions.
So how does shear flow behave in these thin shapes?
It's quite elegant, actually. The shear flow Q always acts parallel to the walls of the member. It literally flows along the thin walls.
Okay.
And how it changes is interesting. It tends to vary linearly along segments that are perpendicular to the main shear force direction, like the top and bottom flanges of an I-beam or channel.
Linearly, like a straight line increase or decrease.
Yes, but it varies parabolically along segments that are parallel or inclined to the shear force direction, like the vertical web of an I-beam or the slanted sides of a trapezoid.
Parabolically, like the stress distribution in a rectangle.
Yeah.
Okay, so what direction does it flow? Is there a pattern?
There is, and visualizing it helps a lot. Imagine the shear force V acting downwards on, say, an I-beam cross-section.
Yep.
The shear flow Q seems to start at the outer edges of the top flange and flow inwards toward the web.
Okay, coming in from the sides.
Then the flows from both sides of the flange combine and flow down through the web. This downward flow in the web is what primarily balances the external shear force V.
So the web is carrying the main load downward.
Primarily, yes.
Mm.
Then, at the bottom flange, the flow separates again and flows outwards towards the edges of the bottom flange.
So in at the top, down through the middle, out at the bottom, like a current.
Exactly like a current. This visualization helps you determine the direction of the shear flow, and therefore the shear stress, at any point in the thin wall.
Let's take a thin-walled box beam as an example. Say it has a 50 kilonewton shear force acting down.
Okay, a square rectangular tube.
How would the shear flow look?
Well, along the top horizontal wall, it would likely start at 0 at the corners,
Yeah.
then increase linearly towards the middle, maybe reaching, say, 97 kilonewtons per meter if you calculated it.
And it flows down the vertical side walls.
Yes, and down the side walls, it would vary parabolically, starting at that 97 value at the top corner, likely increasing to a maximum value at the mid-height, maybe 166 kilometers.
And then decreasing back down towards the bottom corner.
Correct, following that parabolic curve. And then it would flow outwards along the bottom wall, mirroring the top, but in the opposite direction. This calculated distribution shows that linear variation on horizontal parts and parabolic on vertical parts.
That's a really clear picture of how the force navigates the shape.
It is. Understanding that flow is key for thin-wall design.
Now, there's one more really crucial concept related to shear, especially in non-symmetrical shapes, something called the shear center. Let's talk about twisting.
Ah, yes, twisting due to shear, a major headache if you don't account for it.
Take a common shape like a channel section, a C shape.
Yep, very common.
If you just apply a simple downward force right through the middle of the C, the centroid,
Yeah,
what happens? You'd think it just bends down.
you'd think so, but it doesn't. It bends down and it twists.
It twists. Why does it do that?
It's because of that shear flow we just talked about. The shear flow circulating through the flanges in the web creates internal forces.
Okay.
In a symmetrical shape like an I-beam, those internal forces are balanced. But in an asymmetrical shape like a channel, the resultant forces from the shear flow in the flanges create a net torque or twisting moment about the centroid.
So the internal forces themselves cause a twist, even if the external load is straight down the middle.
Exactly. The internal shear forces aren't balanced around the geometric center.
That sounds like a big problem for structural stability. How do engineers prevent that unwanted twisting?
They use the concept of the shear center, sometimes called the flexural center. Let's call it O.
The shear center, oh, what is it?
It's a unique point in the cross-section. If you apply the shear force V through this specific point O, the beam will bend downwards without any twisting.
Ah, the magic no twist point. How does that work?
It works because the shear center O is located such that the moment caused by the applied force V exactly balances the internal twisting moment generated by the shear flow forces in the flanges and web.
So if you push through O, the internal twist tendency is canceled out.
Perfectly canceled out. The net moment about O from all the internal shear forces is 0.
That's clever. Does the location of this shear center depend on the load?
No, and that's what's really useful. The location of the shear center depends only on the geometry of the cross-section itself, not on how much load you apply or where it comes from.
So every shape has its own unique shear center location.
Every shape does. And another key property. The shear center always lies on any axis of symmetry the cross-section might have.
Okay, so if a shape is symmetrical.
If it has one axis of symmetry, the shear center is somewhere along that line. If it has two axes of symmetry like an I-beam or a rectangle or a circular tube,
Yeah.
then the shear center is right at the intersection of those two axes of symmetry, which happens to be...
The centroid.
Exactly. So for doubly symmetric shapes, the centroid and the shear center are the same point. That's why you can load an I-beam through its center and it bends without twisting.
But for something like a channel, which only has one axis of symmetry horizontally through the web, the shear center won't be at the centroid.
Correct. It will be on that horizontal axis of symmetry, but shifted sideways from the centroid out away from the web usually.
How do engineers find its exact location?
There's a procedure. First, you figure out the shear flow Q distribution around the section, assuming it bends without twisting.
Okay.
Then you calculate the resultant forces from that shear flow in each part, like the force in the top flange, FF, the force in the bottom flange, FF, and the vertical force in the web, which should equal V.
Right.
Then you pick a convenient point, often a point on the web, and sum the moments of those internal forces, like F times its lever arm, about that point.
Yeah.
This internal moment must be balanced by the moment of the external force V applied at the shear center, which is V times the unknown distance to the shear center.
So you set the internal moment equal to V times E and solve for E.
That's the essence of it. You solve for that eccentric distance E, which tells you exactly how far the shear center is from your reference point, like the web.
Let's take that channel section again. They calculate E. What does that tell the designer?
It tells them, if you want this channel to bend without twisting, you must apply the load along a line that is offset by distance E from the web, or you need to brace it or design connections to resist the inherent twisting tendency if the load isn't applied through the shear center.
So it dictates where the load path should ideally be.
Precisely. It's critical for stability, especially in open sections like channels.
What about an angle section, like an L shape with equal legs? Where is its shear center?
The equal leg angle is a fascinating case. It also only has one axis of symmetry, diagonal, but its shear center turns out to be right at the corner where the two legs meet.
Right at the corner. Why there?
Think about the shear flow. It flows along each leg. The resultant shear force in each leg acts along the center line of that leg. Since the legs are equal, these two resultant forces are equal, and their lines of action intersect right at the corner. Meaning they create zero net moment about that corner point. So if you apply the load V through the corner, there's no net internal torque and therefore no twisting. The corner is the shear center for an equal leg angle.
That's neat. Built right into the geometry.
It really is an elegant result.
Wow. We've really covered a lot of ground today, haven't we? It feels like we've peeled back some layers on how structures work.
We certainly have. We started with just understanding that basic push across a beam transverse shear and how it creates that hidden partner, longitudinal shear.
Visualizing those forces, seeing them in things like splitting railroad ties or needing glue between boards.
Then we tackled the shear formula. T equal is VQI, mighty, but with those important footnotes about its assumptions and where it's most accurate.
Understanding the V, the I, the T, and especially that Q term, the moment of the area trying to slide.
And seeing how that formula explains failure modes in timber or stress distribution in steel beams.
Then we move to shear flow, Q, for built-up members. How VQI tells us the force per length needed for connections.
Leading directly to practical things like calculating nail spacing, SEFQ, and realizing how just changing the arrangement of parts can drastically affect strength.
We visualize that flow in thin-walled sections, seeing it move linearly and parabolically, channeling the force through the shape.
In at the top, down the web, out at the bottom, that intuitive picture.
And finally, we landed on the shear center. That critical point O that lets engineers design beams, especially asymmetric ones, to bend without that unwanted, potentially dangerous twisting.
Finding that balance point where the internal shear forces don't create a net torque.
These ideas, shear stress, shear flow, shear center, they really are fundamental, aren't they?
Absolutely fundamental. They underpin the design of almost everything structural around us. The beams in your house, bridges, airplanes, even complex machine parts.
Understanding them is really key to making sure things are safe, predictable, and work the way they're supposed to.
Without question. It's about managing those internal forces effectively.
So, as a final thought for you listening, Think about something maybe a bit more complex structurally. Maybe a modern bicycle frame with its oddly shaped tubes, or the intricate structure of a skyscraper's facade.
Good examples. Often quite asymmetrical.
Given what we've discussed today about shear flow, and especially the shear center, what new questions might you ask about how those structures are designed? How do they manage the shear forces and prevent twisting, particularly with those unique cross-sections? Something to ponder next time you see one.